plane, and we're going to do Cartesian as well, is not that far off from what we've been doing. So once upon a time, we have some position vector A, right? So just like last time, we had some position vector A, right? And let P and Q be two non-zero vectors, which are not in the same or opposite direction. So they're not parallel, they're not perpendicular, because if they are, it'll collapse back down into a line. So think of a plane out in 3D, in space, right? So you have, let's say you have this vector P, and let's say you have this other vector Q out in space. That's a Q. Yay? Okay, so if you take a look at those vectors, those two blue vectors, right, and just make a couple more parallel lines, you can see that it can be made into a plane. They can describe some plane out in space. Okay? Okay, and let's say where that point means, let's say this point right here, where they're connected to vector A, let's say that's point A. Right? And let's say this is point R. Yay? So if they're at the origin right here, then the vector that connects to point R is like vector R. And wouldn't you say that vector R is like vector P plus vector Q? Yay? Plus A, the position vector. So, considering scalars, just like before, we had A is equal to lambda plus P, right? Now we just have this third component, Q. That's it. So the vector equation goes something like this. R this time, you still have your position vector A plus some scalar of P plus some scalar of Q. So you just need a direction vector for P and Q just like last time. Yeah? One more component. That's it. That's it. Yeah. Okay. The Cartesian equation is similar to that from last time. All right. So let n be the perpendicular to the plane. And normal. Very good. So we're calling this the normal to the plane, right? Okay, so we need a plane. Yeah. Okay. And let n be normal to that plane, right? So n is normal to some other vector that's laying on the plane. Let's say the point that touch on the plane is P, and some point on the vector on the plane is R, right? So n is normal to that vector PR, which could also be written as R minus P, the vector R minus P. Okay. You need a position vector that goes to that point on the plane. So let's say this is the position vector. Let me pause real quick for Mr. Degnan. Hello, sir. Welcome. Let me pause this video real quick.
I know you hate to have me turn you away from
Oh,
the question.
you know what? It's a... see, that was... Where were we? Here we go. We're describing the Cartesian equation of a plane. That's the origin. Yay. This is vector P to get to that point, and this is the vector R to get to that point. Okay? The beautiful part about the normal is that it's perpendicular to some line on the plane, so the cross product is 0, right? So this is how it comes up. Remember, Cartesian equation just has x, y's, and z's in it. So if RP is a vector parallel to the plane perpendicular to n, then R minus P dot n is equal to 0, right? Using that distributive rule, you can go R dot n minus P dot n is equal to 0. So R dot N is equal to P dot N. True? Right? Now, if you let R be X, Y, Z, and N be A, B, C. So, in other words, the normal is they're just the coefficients of the Cartesian equation of the plane. So it's really easy to pick out. Then this equation becomes X, Y, Z dot A, B, C equals P and N, which is a constant. So since this is a constant, yeah, it's going to be D. It's going to be some constant. Yay? AKA AX plus BY plus CZ equals D is the equation, Cartesian equation. So, yeah. Normal is pretty easy to pull out. Just pull out the coefficients. Yay? All right, we'll get back to this one in a second. Because now all this does is just add more ways, more variety in how to solve these things. All right. Yeah. How you go back from Cartesian to vector? If you have this part, then you can figure out what your X, Y, and Z is your R, and then just use your coefficients to be A, B, C, and then it just goes right back up to it. We'll look at one. Okay? Okay, I'm pretty sure there's an example on that one. Okay? All right. Here we go. Oh, yeah, that's normal. Okay. Yeah, sorry about the copies. Here we go. Find the position vector of point A where the line meets the plane. Yay? Love these things, because when the line meets the plane, that just makes them equal. True? Yep, so set them equal to each other since they're both R. So 2 plus 4k, negative 1 minus 6k, and then 2 plus k. Like that is equal to 1 plus 0 lambda plus mu, and then 0 plus lambda minus mu, and negative 1 plus lambda plus 0 mu. No mu. Yeah? Which just gives us, if you were to get all the constants on one side, you would get 4k minus mu is equal to negative 1. 6k plus lambda minus mu is equal to negative 1. And then k minus mu is equal to negative 3. All I did was just move the constants to the other side. It's true. Okay. Then just using row reduction. P.S. Does anyone know how to do it like calculator? Do row reduction? Okay. After this lesson, let's see if I can figure it out. It's been a while. I did it in college. But yeah, there's a way to just type it in your calculator. And this one, Miss Wass taught you a long time how to do row reduction. Yeah. We'll try it again. Try it again. What were you gonna say, Alejandro? MS? Oh well, you know, I don't want a chance to listen. All right. Here we go. Okay, so using the method of triangulation, how about for the second row we go 2 row 1 minus 3 row 3. I'm sorry, 2 row 2 minus 3 row 1. Yeah? And then the second one we could just go 4 row 2 minus row 1. 3 minus row 1. Thank you, sir. Yeah, just getting rid of the k's. Sweet. That leaves us with 4k minus mu equals negative 1. And then 2 lambda plus mu. Right? And then I got negative 4 lambda plus mu equals negative 11. Okay. So? Yeah. Yep. So row, whichever. Oh, ouch. Okay. What do you want me to do? Row 2 by row 3? Okay. I like to get rid of that last row. Just saying. Row 3 minus row 2. Yeah. And that leaves us with 4k minus mu equals -1, 2 lambda plus mu equals 1, and then -6 lambda equals -12. So this tells us that lambda is 2. Plug in 2 to here, 4. So mu is, yeah, and k is -1. Yeah, to where? Yeah, that's it. Yeah, if you just pick the k, since k is -1, just plug it into that first equation. So the point of intersection has vector 2, -1, 2, plus -1, 4, -6, 1. Which gives you -2, 5, 1. And the coordinates are -2, 5, and then 1. Oopsies. Yay? Yay. Okay. All right. What examples are there? Okay. Ready? Okay. Cartesian equation with a plane through the point, blah and blah. What does a Cartesian equation look like? What does a Cartesian equation look like? Yeah. AX plus BY plus CZ equals D. True? Okay. So if the normal is 4, 5, 6 with 1, 2, 3, isn't this X, Y, Z, and isn't this A, B, C? True? Only thing we don't have is D. All right, here we go. So 4 times 1 plus 2 times 5 plus 6 times 3, 32, which is D. So the Cartesian equation is, heavens yes, joy. I mean, yeah. Okay. All right. This is the part where in example 3, there's so many ways to handle this. Right. First of all, in example 3, really quick, I negated to put a minus here. I tried to work it out without the minus, but it was one of those situations where it was parallel or perpendicular, one of the two, and so it just collapsed into a line instead of a plane. So without that minus, that's kind of key, because otherwise it wouldn't work out. Yay? Okay. Here we go. So you could do your AX plus BY plus CD, just making all of that like this would be like 1x plus 2y plus 1z equals d, and then like solve for d and that kind of stuff using row reduction. But let's try using the normal thing. Okay. So let A be the position vector. Yeah. Vector 1, 2, 1. That's supposed to have a C in it. There you go. Yay. So wouldn't you say that AB is equal to 2, negative 1, negative 4, minus 1, 2, 1, which is 1, negative 3, negative 5. And then you need another vector. So you have your position vector, and then you need your 2 vectors, right? So that's one vector. The other vector could be like AC. You could also do BA and BC, by the way, if you wanted to. Right? AC would go 1, 0, negative 1, minus 1, 2, 1, which gets you 0, negative 2, negative 2. Yeah? Okay, so you need the position vector, the other 2 vectors, and the normal, which we have no idea what is. So, amen. Do you want to show us that one? Or do you want to see like how they did it? No? Yeah, I'm going to go with PQR for normal. Is that cool? Yeah, just because it goes back to this. Here's what I'm looking at. Right, going back to doing this. Yeah. This one. Ouch. Here we go. So going back to the normal, I'm just going to go PQR, PQR. What I'm trying to prove is this, that the 2 products are equal to each other, kind of thing. Okay. All right. 2. Yeah. Okay. So if you let the normal be some PQR, is it working? And that was too much. That was too much. Okay. I have no idea. It's technology. Let me hit pause. Yes, sir. Yeah. Yeah. Yes. Yes, and that would be your normal. Yeah. Yeah. So let normal n, yeah, be PQR. Yay. So based on, since it's normal to a plane, then the dot products of the normal to each of these should be equal to each other. Yay. So 1, negative 3, negative 5 dot PQR should be the same as 0, negative 2, negative 2. Oh, hello. Dot PQR. It's supposed to be a dot, which we know since it's normal is going to be 0. Sweet. So that gives us 2 equations. Just moving everything to their side, it goes P. Oh, actually, they both equal 0. So P minus 3Q minus 5R is equal to 0, and then negative 2Q minus 2R is equal to 0. This is one of those things where we have 2 equations, but 3 unknowns, so we need a keyword. Parameter, yeah. All right, we need a parameter. So since P is all the way out there, let's let Q be T. Let Q be T, or negative T, I should say. All right, whichever. Woo. Okay. Actually, let R be T. We should probably solve for the first one, or the easiest one. Yeah. Delete that. Okay, so if you let R be T, there you go. Plug in T for this one, and then you would get Q is equal to negative T, and P, plugging it into the last one, you would get P is equal to You? 2t, yeah. Thanks, sir. Yep. Yeah. Right? Since you just need one normal, you can plug in anything for t, right? So if you let t equal 1, this is since you only need one normal. Right? You can let t be whatever you want. That would give you the normal of 2, -1, 1. Would you have gotten that with IJK, IJK? Not sure? We'll take a look at it in a little bit. Yeah. If that works, use it. Okay? Okay? So using A, using the point 1, 2, 1, then we're going to have the equation 2x minus y plus z is equal to some constant k, or d. Probably should have used d. Plugging in the x, y's, and z's of 2, 1, and 1, so it goes 2 times 1 minus 2 plus 1 is equal to 1, which gives us the equation 2x minus y plus z is equal to 1. Can you show me the IJK thing real quick? Okay. All right. Perpendicular distance. They love this one. Expect one on the test. They love it. They love it. They love it. Here we go. Find the perpendicular of the point blah, blah, blah from the plane blah, blah, blah. Okay? What's the normal? You are so smart. Yep. 1, 2, -2. Okay? So, yeah, that's going to be like, your normal is like your direction vector. Okay? So, the line through 4, 5, 6 is perpendicular to the plane, has equation r equals 4, 5, 6. That's your position, plus lambda 1, 2, -2. Remember? If you let r be x, y, z, so x, y, z is equal to 4 plus lambda, 5 plus 2 lambda, and 6 minus 2 lambda. Just plug that, since they all equate to x, y, z, just plug it into that equation. Do this. So you can say that it goes x plus 2y minus 2z, right? So if you plug it into x plus 2y minus 2z equals 9, x is 4 plus lambda, plus 2 times 5 plus 2 lambda, minus 2 times 6 minus 2 lambda is equal to 9. And do you believe me when I say that all of that just reduces down to 2 plus 9 lambda? You believe me? It should work out. Okay? And, yeah, lambda equals 7, lambda equals 7 ninths. Now here's the deal. Lambda is just a scalar, so it's also the scalar of the magnitude. Right? The magnitude is the distance, right? So, let's step back. Yeah. Nick's so smart. The length of vector from 4, 5, 6 is 7/9 the length of vector 1, 2, -2, right? Which is just the magnitude. So the magnitude of that one would be square root of 1 squared plus 2 squared plus -2 squared, which is the square root of 9. Yep. Which is 3, right? So the perpendicular distance is equal to 7/9 times 3, which is 7/3. Yeah. Amen. Did we get to the... Nope, we did not get to that point. All right, if you get to the one where it says go from Cartesian to vector, we'll look at that, because apparently there was an example. Thought there was. Yeah. Yeah. Okay. It's all good. Let's find angles. I love this one too. Here we go. Find the acute angle between the line, blah, and the plane, blah. Yay? Yeah. So, say it again. Switch the y values back to what? You can. It's really easy though. What's the vector direction, do you remember? Like, where do you get the direction vector from this equation?
Oh, the bottom.
It's the bottom ones. Yeah. So the line has direction vector 2, 4, 1. That's like your LK something something, LK and M. LK and M, right? Right? Yeah. We also have the normal. Where's the normal? Yes. ABC. 1, -1, 1. Sweet. So the angle theta between them, yep, them, right, is the dot product. So that has something to do with cosine. Yeah, is cosine theta, and then the cross product, right? So 2, 4, 1 dot 1, -1, 1 divided by the magnitudes. Magnitude of 2, 4, 1. 4 plus 16 plus 1, 21. And then magnitude of 1, 1, 1, Tre, is -1/3√7. So, if you hit second cosine of, where again? Second cosine of -1 divided by square root of 3. Is that, no, sorry, 3√7. Parentheses, 3√7. Yeah. The answer is 1 point something something, which if it, I need the mode to be in degrees. Enter. Second quit. Second enter, so I don't gotta retype it. Do it again. 97. Is that right?
Wait, that's not an acute.
That's not an acute angle.
So we subtract that.
Did I do that right? second cosine of 1 over 3 root 7. Negative 1 over 3 root 7. Yeah. Not 180 actually, to subtract from 90 is what it is. Here's why. Ready? Yeah. Yep. Normally you would subtract from 180, but this one, right the picture. Oh yeah, here you go. So here's the picture of it. Since it is, the normal is 90 degrees to the plane, right? Yeah. Yeah. You like the visual? Yeah. So since the normal is 90 degrees to the plane, you would subtract from 90 if it went anywhere over 90. What is it? 7 is the answer to 42 divided by 6. But what? 7? Oh, yeah. Yeah. Yeah, 7 degrees. Yeah. I think in the book they had it in radians, but it don't matter. It don't matter. Yeah. Let me go back to here. Oops. Right. Yeah. Let me take that 1.697. Yeah. Okay. So, hello. Okay. So this will give you theta is 90, what? Was it 91? 97.23 something degrees. So subtract that from 90, and then you get the actual theta is 7 degrees point something. Yeah, it's about 7 degrees or whatever it is in radians. Yay? Nay? Alright. They love this one. It's not hard. Yeah. Okay. Ooh. Find the nearest degree of the angle between the two planes. Oh, what is that? The 1, 2, negative 1. What is that? Yeah. The normal to that one is 1, 2, negative 1. 2, negative 5, negative 4. Dot product, divide. Wow. Right? So cosine theta is, 1, 2, negative 1, dot 2, negative 5, negative 4, divided by. All right. 1 plus 4 plus 1. What? 1 plus, 6. And 44. 45. This is 45. Ask your parents. Do you believe me when I say it's negative 4 over the square root of 270? Sure. Which is what degrees? Do you have a calculator? I do. Just let me make sure this is correct. Right. Second cosine of negative 4 divided by the square root 270. 104-ish? 104-ish? I like 104-ish. That's, that's a good one. Yay? Okay. Here we go. Let me pause this really quick, and then I do want to get to, make sure that I don't skip over Matt's original question for the day. Yeah. Right? Let me, pause this.